For a given sequence of positive real numbers, these pn's from n equals 1 all the way up towards infinity, consider the infinite series of adding these up. If we know that the partial sums of this series, these SNs, satisfy the inequality that they are always less than or equal to 57, show that this infinite series converges. So, this is a bit more theoretical. I don't know what the PNs are. I don't have a formula for them. I don't even have a formula for the SNs. If I had a formula for them, I could just ask, does the limit of the SNs exist? But all I currently know about the SNs is no matter what the index n is, and no matter how many terms in my sequence I add on, my partial sums are always going to be less than or equal to 57. Now we are being told the answer. We want to show it converges. Okay? And that's a dangerous thing sometimes in questions where they tell you, show that this specific thing happens. Because you can very easily convince yourself that you have actually shown it, because you know what the conclusion should be. You know what the right answer is. We should end with, therefore, it converges. Okay? And so we accidentally convince ourselves that a step that we take is correct when it isn't, okay, we will end up botching this. This won't go well for us. So we want to show that this converges. Okay, well, it converges only if the limit of the partial sums exists. Okay, now, since I have no idea what the PNs are, okay, maybe we should try and show the limit of the SNs exists. Okay, but that's going to be kind of hard if we don't have a formula for the SNs. In fact, we only know two things here. The PNs are always positive, and the SNs are always less than or equal to 57. Okay. Now, when we look at that, we say, well, the SNs, they've got sort of a ceiling. They can't go past the 57. Right? They are bounded above. There's an upper bound. There's a line. Do not cross. You cannot go above this. So it makes me think maybe we could use a result that might incorporate an inequality like this. The monotone convergence theorem, or MCT, okay, says if we can show the SNs are bounded, the partial sums are bounded, and monotone, so all heading in the same direction, then the limit of the SNs would exist. We wouldn't necessarily know what it is. You know, maybe it's 57, maybe it's something much smaller. Okay, maybe it's negative. I have no idea. I mean, it's probably not negative because I've got a rough plan as to where I'm going with this. Okay? But I don't need to know what the limit is if I use a result that just says, show these things and the limit exists. And as soon as that limit exists, I know that the series will converge because that's the definition. Okay? Infinite series converges if the limit of the partial sums exists. You don't need to know what that limit is, you just need to know that it exists. Okay? So bringing a result like the monotone convergence theorem into play means I have some things I can try and do. I can try and show the SNs are bounded. Okay? I already know there's an upper limit. Okay? Can I show that they must be greater than or equal to something? Maybe greater than or equal to 3, something like that. That would show that it's bounded. Okay, and then monotone. How will we show that they're monotone? Well, first we'd have to sort of get a sense of what's going on. Now, we don't have really any properties other than these two. Okay, as we already said, we know the PNs are positive, but we do know that the PNs relate to the partial sums. We do know that we can, for example, write S1 as P1. S2 is P1 plus P2. S3 is P1 plus P2 plus P3. So there is a relationship between the positive sequence that we're given and the partial sums. Okay. Now, is there a way to use the fact that the sequence is positive? How do you go from S1 to S2? Well, you just add on P2. How do you go from S2 to S3? Well, you just add on P3. So S2 is P2 plus S1. S3 is P3 plus S2. So to get the next term in the partial sum sequence, we are adding on the next P, Pn. But those are positive. Okay? So here's what I'm going to say. Notice that Sn plus 1 is Pn plus 1 plus Pn plus, I'm writing them backwards, I guess. But this is Pn plus 1 plus Sn. So rearranging this, we see that Sn plus 1 minus Sn should just be the Pn plus 1. And I don't know a lot about the P sequence, but I know it's positive. So Sn plus 1 minus Sn is positive. And rearranging that once again, we can see that the Sn plus 1, the n plus first partial sum, is greater than the nth partial sum. So the Sns are strictly increasing. Well, that's great. Increasing is a kind of monotone. It can be increasing, strictly increasing, decreasing, strictly decreasing. Okay. So when it comes to the monotone convergence theorem, we've got the monotone already done. Okay. Now let's think further about our sequence. We know it goes S1, S2, and we're increasing, so S4 is greater than S3, S5 is greater, S6 is greater. They're going up and up and up. Okay, so we can see that every term here is at least as big as S1. Or you could say, since S1 is really P1 and they're always positive, you could even say that all of these are non-negative. They're all greater than or equal to 0. Okay. But we also know that as we keep going on, there's a limit. We can't go past 57. Because no matter what n is, the nth partial sum, they tell us, is less than or equal to 57. So we see the Sn sequence is also bounded. And that's it. That's the last thing we needed to show. So what would we say? By monotone convergence theorem, the limit of the Sns exists. So the sum of the Pn's, well, it does exist, but we should be saying converges. All right. Just had to be a little creative because we didn't have any actual formulas, so we had to rely on properties and results, like our good friend, the monotone convergence theorem.